Hi, Eric.
Hello.
Good morning.
Morning.
Thanks for joining.
Sure, it's a beautiful day today.
Yeah, it's in the Bay Area.
Yeah, in the Bay Area, it's very sunny.
Up here, all we have are clouds.
Where are you at? In Seattle?
Seattle.
Oh, okay. All right, let's give it a couple more minutes, see if more people join, and then we can get started. I posted the meeting notes URL on the Zoom chat, and if you can, add yourself as an attendee today. All right, I think we got a good number of people. Thanks everyone for joining. So today we have a couple of agenda topics. First, we have INNATIVE. So we have Eric. He'll be presenting the project. I think it's. I mean, happy to learn more about it, but I think it's just-in-time assembly runtime, or so that you can embed WebAssembly. Sorry, WebAssembly runtime that you can embed these WebAssembly modules in some devices at the edge. So yeah, so happy to learn more about it, and yeah, take it away.
All right, so I'm Eric McClure. I'm from Fundament Software, and we're the ones who have made INNATIVE. INNATIVE is a proof of concept ahead of time WebAssembly compiler built on LLVM. It does have a just-in-time component, but the primary purpose of INNATIVE was to find out what benefits ahead of time compiling would bring to WebAssembly. It is used in Microsoft Flight Simulator 2020. I don't know if anyone else is using it, but it has no real actual runtime. It only has a shim to do the operating system syscalls. And so anyone using INNATIVE actually has to provide their own runtime. This is usually an implementation of WASI. In the case of Microsoft Flight Simulator 2020, they actually had their own implementation of the WASI interface that was specifically designed for their plugin interface. But it's designed to participate in the C linking process because it's not a traditional JIT. It doesn't assume the presence of a virtual machine or anything like that. It actually compiles down to a completely self-contained DLL or executable that can be used just like a normal library in Windows or Linux. And because of it, it still emits debug information inside the executable on Linux or in a PDB on Windows. And more interestingly, it gives you options for the level of sandboxing that you actually want. So it has the complete strict implementation of a standard, a sandbox that only implements things like memory sandboxing for security, or there's no sandbox. There can be no sandboxing at all. And one of the major questions we wanted to answer, well, we wanted to explore basically, was how is WebAssembly viable as a universal binary? And the question is, how fast is WebAssembly without sandboxing? And the answer is very. In here, we can see that this is just a standard benchmark comparing a native C++ compilation of some benchmarks on the left, which is our baseline at 1.0. A debug, which is very slow because it's got all the debug information running at 38% of the C++. Our strict implementation of the WebAssembly standard running at about 85%. And I will note that other runtimes that actually intend to optimize for running inside a sandbox get much better times than this for their sandboxes. But for native, we reach 96% on average native speed for benchmarks and other stuff that we're running. And this is without, because there has been a WebAssembly SIMD extension that was ratified, but is not quite in production yet. The hope is that once compilers support Emscripten and all the other WebAssembly compilers support that we can push this 96% to something like 98% or 99% and recover almost all the native performance of a normal executable from WebAssembly, which is very interesting because this means that WebAssembly could be a viable way to ship existing software to multiple architectures with like almost no perf impact. And this is not usually talked about as an application of WebAssembly. Every single time I've talked to people about it, it's all about the sandboxing opportunities, which are nice. It is very nice to have a convenient way of shipping a sandboxed application without having to use containers or VMs or whatever. But it's also interesting to talk about it from the perspective of existing software today that does not have sandboxing, that still needs to ship to different architectures and be recompiled with various different, make decisions about which CPU features they're going to require. For example, a famous example was No Man's Sky when they accidentally shipped with SSE 4.2 and then they couldn't run on a whole bunch of AMD processors, which was a problem. WASM is also working on this, but they're taking the approach of a jitting WASM runtime using cargo lift, the last time I checked. And they're also trying to approach this. They're trying to design a way of creating a universal binary that you can ship across all systems. And so INNATIVE is mostly approaching this from the perspective of architecture, but WASM was pushing WASI, the standard system interface, so that you could actually ship the same executable to completely different systems. And that's a kind of out of scope for INNATIVE for right now. But that's just how the rest of the WebAssembly industry is. There are various different approaches to how universal is universal, basically.
A question. So when can I? Yeah, I ask a question. So when you compile this, you can only ship it to a certain type of CPU, or is it?
It depends on how you're using it.
Mm-hmm.
Well, it depends on how you're using it. So when INNATIVE is compiling, INNATIVE basically gives you a tool for compiling WebAssembly to a particular architecture and using a particular environment. That environment could be WASI, and it could be whatever architecture we happen to have support for. Right now, it's only x86, but eventually we're going to add ARM support and possibly some other architectures. So,
it's not necessarily tied to the CPU at a low level, because you had mentioned like it's something that Intel was working on Intel, but not necessarily working on AMD, but just either x86 or ARM and WASI basically.
Yes. So, I mean, obviously INNATIVE is not tied to anything, but what INNATIVE can do is, because it receives the WebAssembly binary on the target machine, it can compile that WebAssembly binary specifically for that CPU using all possible CPU features for optimization, instead of the traditional way of shipping software, or well, desktop software, where you have to pick which CPU features you're going to ship for, because everyone gets the same binary. So if you pick, features that aren't on old CPUs like SSE4, then you're going to run into trouble with people who have old CPUs, or in the case of No Man's Sky, it was SSE 4.2, which AMD did not support on their machines, because it's a very specific set of instructions that only Intel was supporting at the time.
Got it. Thanks.
So the intended use cases of INNATIVE are generally on devices without JIT. INNATIVE does include a JIT, a primitive JIT with LLVM using the ORC2 JIT system, and this is mostly intended for development. So it makes it easier for developers using INNATIVE to rapidly iterate. But the whole point of Microsoft Flight Simulator 2020 using INNATIVE was because they needed to ship Microsoft Flight Simulator on the Xbox. And the reason the Flight Simulator is using this at all is because of a plugin system. So all the planes in the Flight Simulator are actually arbitrary code. They used to be just DLL files that were shipped with the game. But with the new 2020 version, they wanted to do this with WebAssembly, which is cool, except that the Xbox doesn't let you JIT because you can't allocate an executable page. So they basically had to turn to INNATIVE to have an ahead of time WebAssembly compiler that could take their WebAssembly and compile it to a binary using their custom embedding. Someone say something? Using their custom embedding that they can then ship with Xbox as well as on desktop. And in addition to this, we're also looking at embedded devices that can't really afford to JIT WebAssembly right on top of the device, like a Raspberry Pi or IoT devices. And we've recently added cross-compilation to the unstable branch. And so the hope is that we will be adding ARM support soon, and then we can test out deploying WebAssembly to IoT devices without needing a runtime or a JIT or anything like that. But that's still upcoming. Another interesting application are high-trust WASM programs that can run without a sandbox on a desktop, because we have lots of programs that we let run amok on our systems with no sandboxing other than the kernel. So an interesting use case might be running WASM inside Electron instead of JavaScript, which could have huge performance benefits, which is a very interesting possibility because Electron exists essentially to remove the sandbox around JavaScript and allow it to interact with the operating system. That's the entire point. So running WASM inside of Electron, we don't even know what the performance benefits of that could be. I mean, right now, unfortunately, if you try and run WASM inside Electron, you're just going to get the sandboxed WebAssembly anyway. But in addition to that, INNATIVE has no mandatory runtime. What it ships with is a very tiny shim over the system calls in order to implement memory.grow and the atomic instructions. So all it's doing is simply maintaining the barest minimum information necessary to allocate a heap and and assign this to a linear memory in WebAssembly. Now, this is not useful by itself, which is why it also allows linking to arbitrary C libraries as embeddings. And these C libraries can be interfaced with from whatever WebAssembly you are compiling. So this means you don't so basically most like WASM or WASM time, all of these WebAssembly runtimes tend to assume that you are targeting WASI, which is handy most of the time, but it's not great for game plugins, which is one reason why Flight Simulator wanted INNATIVE. And this means that games do not have to use WASI. They can, if they want to, they can provide WASI, or they can provide their own environment inside for the WebAssembly module to execute inside of, and only expose whatever functions are in there. But it's still compatible with the WASI embeddings, even though it does not ship with an implementation yet. And we have basically INNATIVE has a start point parameter in order to participate with WASI's custom rules about how WebAssembly is supposed to work, which basically add additional assumptions on top of the WebAssembly standard. However, I have run into an issue where some WASI implementations don't include the entry point logic for the operating system for dealing with command line arguments, because WASI has its own definition of the entry point that includes command line arguments, and the WebAssembly itself just has an empty entry point. So there still needs to be additional work for that. Additionally, it is not clear how this will extend to the garbage collection proposal that is still going through, because a garbage collector, if garbage collection support is added to WebAssembly, then there will be basic WebAssembly instructions, fundamental WebAssembly instructions that require a garbage collector, which would require the minimum runtime to ship an entire garbage collector, which is not entirely ideal from this perspective, and also wouldn't be ideal for situations like IoT devices that might want to be using WebAssembly. So we may have something like, we would have to wait until the GC proposal is more mature, but we would probably put in something like a flag that says, yes, support garbage collection, or no, do not support garbage collection.
One question, what is so for standard ahead of time compilation, you ship the game plugins. So the entry point for those is just the flight simulator application, and
it's whatever you want. Well, it's a plugin, it has no entry point.
Right.
There is a hook on when you load the DLL that initializes the memory correctly.
Got it. And what if you don't want to have a plugin? So what would be the entry point? It's just,
oh, well, an executable sets the entry point too. So the way INNATIVE does it right now is it strictly adheres to the standard, where the standard set points to a function that takes no arguments and returns nothing as the entry point, and that is set that is passed to the linker as the entry point to the executable.
see. Okay.
So the only thing that you'd have to change for WASI is you'd have to put in a shim have the entry point point to a shim function that gets the operating system command line. So like on Windows, it would acquire the command line. On Linux, it would do the same thing. And then it would it would create the string allocations and pass those into the WASI entry point.
Got it. Thanks.
But yeah, speaking of that, this uses everything that it compiles is standard C linkage. So all the entry points have direct analogs to the actual entry points that you would find in a normal executable, and it uses a standardized name mingling function to allow for linking between different WebAssembly modules. So you can have a native like compile one module to a DLL and or compile, say, an executable to compile an executable on one computer, and then later on have it compile a plugin for it. And that plugin would simply be loadable in that executable, just like a normal C DLL. There's nothing else that would be required. There's no runtime that has to be loaded. It just works because it is a standard C compliant DLL or shared library as it would work on Linux. And this means that the C program, any C program, can actually directly link against WebAssembly exported functions if they know what the mangled name is. This is kind of like how C++ works. So if you have a C program, you can call C++ functions if you know how the name has been mangled. And in this case, you can call the WebAssembly functions if you know their type signature and you know how what the mangled name was that was actually exported, which is very useful because now you can essentially, so for scripting languages like Lua, oftentimes they will have C libraries that they interface with in order to do low-level operations. And this is the same idea where you can now include not just as you can mix and match WebAssembly modules with C DLLs and shared libraries. Like there is no restriction on how these can on the interaction here, at least not right now. And this is really cool because that means you can basically have random DLLs be WebAssembly and nothing actually, the linker doesn't care. It will link them all together and it will just work. And to help with this, it exports the standard CDECL calling convention wrapper functions around the internal one. And this is supposed to facilitate allowing the WebAssembly compiler to use a fast internal calling convention that does not actually break allowing a C program to interact with the WebAssembly through the C ABI. And so the internal calls can use their own calling convention and do crazy weird stuff to be optimized. And this is one reason we're able to get such like really good performance, because we can basically turn on all possible optimizations without breaking compatibility with C. However, this does have to be turned off if the host needs to extract function pointers to internal WebAssembly functions due to how WebAssembly tables work. This is the case for the flight simulator, which has their own way of doing hooks that's very weird. And basically, they need access to the internal function pointers that are being passed around in their plugin. So we have to disable, we have to basically make it so that all the WebAssembly generated functions use the standard C calling convention so that they can do that. But as I mentioned before, it uses the proper entry points for shared libraries on Linux and Windows in order to initialize the WASM memory. And this is why you don't have to worry about loading a WebAssembly DLL and having to do cleanup or anything like that. It automatically, when it loads the DLL or shared library, it calls the initialization, and when it's unloaded, it will deallocate everything just like a normal shared library. So INNATIVE also emits debugging information, but it has run into a lot of issues. And the reason for this is because standard WebAssembly debugging presumes the existence of a virtual machine. And this lets them get around a whole lot of issues because we don't have a runtime. We are emitting completely raw, like machine code with no runtime, just shim calls over the operating system. And that means we have to teach a debugger what a WASM pointer is, which is difficult because a WebAssembly pointer is actually an offset to a pointer in memory, the linear memory pointer, which itself could be anything. It is not locked to any particular position in memory. And this is made even more frustrating because LLVM does not support Dorf trampolines or the op address extension for Dorf, which would make all of this a lot easier because this is exactly the op address is exactly for this situation where you append this to a pointer type and the debugger then goes through then executes the instructions to actually find the real pointer. It has been suggested to use the form TLS address for globals, but it is not clear if this can extend to locals or other pointers. So on Windows, we abuse NatViz to convince the debugger to traverse the WASM pointers. We emit a minimal PDB that does not actually contain usable debug information, but it contains enough metadata about that debug information that we can use an embedded NatViz XML file, which is Visual Studio's way of extending its debugger visualizer, and that makes it so that the visualization you see in Visual Studio is the correct values, because the visualizer will actually go through the necessary hoops to figure out what the real memory is for a WebAssembly pointer instead of the actual debug information. It's not clear if PDB is even capable of doing this because nobody really understands how PDB works. It's only the reverse engineered stuff that LLVM figured out. Unfortunately, because we're just abusing the visualizer, virtual inheritance and other complex C++ things just cannot be represented, and it will just die. It can't deal with with complex inheritance stuff. Theoretically, Dorf should be able to represent all of this if we could essentially emit the proper Dorf operations to resolve all of this, but LLVM doesn't seem to support that, so we're stuck here, and this has been a persistent issue. Hopefully this will get resolved in the future somehow, but the debugging issue is mostly that everyone just assumes that the runtime exists. So if you're debugging C++ in Chrome, that's why it works. As I said before, INNATIVE lets you choose what level of sandboxing you want. The sandboxing levels are optional. You can, for example, care about the tail call requirements that are currently in the standard, or just say, I don't actually care about, someone being able to do a Stack Overflow or not, and just sandbox memory to make sure they don't run rampant over your operating system. This has been explored in proof of concept kernels like Nebulet, where Nebulet runs WebAssembly in ring 0 and then isolates and then uses the kernel paging techniques to isolate it from the other WebAssembly modules. There's also VMs that are run unikernels that are running under hypervisors, and these all run higher level sandboxes. So if your WebAssembly module is the only thing running in that unikernel, or you just don't care about what it can access, then you don't need the WebAssembly sandbox at all. And I mentioned previously about Electron and how it unsandboxes JavaScript so it can interact with the operating system. And this is another case where if you're running something in Electron, there is no sandbox. So if you're running WebAssembly in Electron on the desktop, there's no actual reason to sandbox it because it can interact with the operating system anyway. So it would be very interesting to see someone implement WebAssembly in Electron without a sandbox. But I don't know if anyone will ever actually do that. But that's it. So I answered a couple of questions in the middle of that, but now it's, any other questions people can ask.
So have you gotten any more use cases besides Flight Simulator or some other folks interested in using the project?
We haven't had any commercial interest. We've had some hobbyists. Well, one of the reasons we added cross-compilation support recently was because some hobbyists were interested in trying to get WebAssembly on some IoT devices and embedded devices. And the only way to do that would basically be through INNATIVE and cross-compiling to that device. The problem is that we have to add support for ARM in the architecture shim. So we've only gotten like halfway there.
So would it potentially perform better than just WASI WebAssembly, I suppose, in ARM as well, right? So I think maybe if some users would want to deploy, AI type of workloads at the edge, then it would be like a pretty good use case.
Possibly. It kind of depends. I know that because it's hard to tell, because I know that some of the other WebAssembly runtimes have been looking into ahead of time compilation, but from what I know, they still require a runtime, and I don't know if that impacts their speed at all. I don't really think it will, or if that's a concern for things like AI. So like if you're running this on like a really powerful computer or something, or on a bunch of cloud deployed cloud servers for AI, you might end up just using one of the ahead of time options that have a runtime, because you don't care about the memory costs or anything. But I'm not really sure. I mean, you could certainly use INNATIVE for that. I'm just not anticipating people necessarily using it for that, because there are other options right now.
Got it. Cool. Any other questions for Eric from the audience? One more thing. Do you plan to eventually donate this to something like the CNCF, or there are no plans as of yet, because
So what?
CNCF, so donate, it's an open source project, right? So so the CNCF is foundation that hosts open source projects, and so the idea is that when some of these projects actually join the foundation, they get more exposure, so the community sees what the value is, and they can get more contribution basically, and they can help the project mature more basically. Does that make sense?
I guess. I mean, I didn't know about it, so.
Okay, yeah. So yeah, so this is so we're TAG-Runtime, and so we're one of the advisory groups to the TOC. The TOC, the CNCF, is a technical oversight committee. So they actually decide who or which projects actually can join the foundation. And then so we have different stages of projects. We have SANDBOX, we have incubation, we have graduation or graduated projects. So initially, most projects join as a SANDBOX project, and that's kind of like a place where they can get more exposure and where projects can grow, and eventually, if they mature enough, they can apply for the incubation stage, and then so forth. After that, then they can apply for graduation, and then there's different criteria. Certain number of users, certain number of committers or people contributing. Most of the stuff is actually documented on the CNCF GitHub repository.
Okay.
Makes sense?
Yeah. I mean, I could look into that.
Yeah, so it's something to keep in mind. I mean, it doesn't have to happen, but I mean, it's just letting you know that it's available.
Okay.
Okay, thank you, Eric. So I think we have another item on the agenda. We have, let me double check. So we have QoS improvements, memory bandwidth, and block IO classes from Marcus and Antti.
Yep, that's right. This is Antti speaking. And maybe I'll start sharing it so that you could see the slideware as well.
All right, sounds good.
Yeah, hello, this is Markus, also from Intel, working as a cloud software engineer there.
Welcome.
Thank you.
Sorry about the delay. I just need to find the slides myself first.
Yeah, I can share if you want.
Okay. Okay. Yeah, that's nice. Thanks, Sasha.
If you want, I can also say some introductional words.
Okay.
All right. We are part of Intel who are working on topics related to resource management. We had some of our internal projects. Well, it's public, it's open source, where we implemented advanced resource controls for many of the resources. But today we wanted to present pieces which is related to block IO and cache, and how we see what it can be merged into runtimes, and how it can in overall help cloud native workloads. So the first problem is what those resources are a bit tricky, and tricky in different sense if we look at it. So to give you a like crash course, what is happening? For cache control, we have part of OCI spec where we can define several parameters. We can have a class ID, we can have L3, L2, and memory bandwidth schemas. But one of the biggest problems with all of this is what all of these data structures is very hardware dependent. It really depends on the kernel. So like different versions of a kernel might have different parameters available. The hardware limits amount of the classes. So you cannot easily add the things to every single container with the different parameters. So you need to have some way how to group them in one sense or another. With block IO, we have quite similar problem. So again, the block IO controller in the C groups evolved over the years. So we had CFS IO scheduler, and now we have a BFS, and so on. Some versions of old kernels, they don't have some parameters, some have more when it's shown in the picture. And here is also interesting setup. What many of the parameters which is related to the devices, they reference exact like device type and node on the node. So if you have a bit heterogeneity in your cluster, so meaning what like different nodes have different setups of a disk or different like RAID controllers and so on, like you cannot use exactly the same parameters to describe if you want to introduce some throttling or just prioritization of the workloads. So when we looked at all of those, we started to think like how we can make those more usable. And we came to the idea of declaring those resources as a classes. By classes, we mean what, like you have a set of parameters which describe particular properties. Like in block IO, it means it's bandwidth and like throttling parameters and priorities. And in case of cache control, it's again similar. You can define slicing of your hardware cache partitions into either exclusive or shared allocations of the caches. You can define in friendly manner this configuration of those parameters. And when we need to have some way to assign containers into those classes. And when we looked at, so when we have this done, I mean, like configuration part, we started to look how we can expose it into Kubernetes world, how it can be shown. And the blueprint, what we actually used for that is coming from the, at the moment, from the seccomp early implementation. So I want to hand over to Marcus and Antti so they can talk about the exact examples of cache configurations or block IO configurations.
Yeah, the idea in the cache configuration is that you just give the configuration file to the container runtime, and it configures the RDT classes, so the hardware according to the configuration file. So this is just one simple example, kind of mapping to Kubernetes QoS classes, or mapping the Kubernetes QoS classes to RDT classes, so that, for example, kubelet could assign automatically containers to certain RDT classes based on the QoS class. Just an example. And in this example, I mean, could you back up one slide? So this simple example that the guarantee will get all cache lanes and all memory bandwidth and burstable and best effort, only part of the cache lanes. Then the next example, just about the configuration, is a kind of billing QoS example, which could be kind of user assignable classes. So three levels of SLA or QoS: gold, silver, and bronze. And gold would get like 60% of all cache lanes exclusively, and then the other two classes would share the rest of the 40%, and the bronze only getting 50% of that.
I have a question. So this will be defined in the pod spec or somewhere?
No, this would be something that the container runtime reads at the startup time. So the RDT configuration file, and configures the classes according to this configuration file. And then from the CRI side, or from the kubelet side, you would kind of only be interested in the classes, not the configuration itself. So you would just set that, okay, this container belongs to gold class, and then it would be assigned to the class. But the container runtime would handle configuration of all the configuration details of the hardware and the REST control file system, through which the Linux kernel exposes the hardware. And then the kind of blueprint that we copied from seccomp would be, in the initial phase, to be able to assign containers to these classes via by using container annotations or container annotation and also by user through pod annotations. So there will be one annotation to assign all containers to one class, which is the first one there, and then there would be optional or an option to specify container-specific overrides. For example, in this example, put container 2 in the gold class, and others would get the bronze class. So this would be the user specified by the user in the pod spec, well, as shown in the example.
So Antti, about block.io.
Yeah, okay. This is the block.io configuration then. So similarly to the RDT, where the container runtime loads a special RDT configuration from an RDT configuration file, here is then the block.io configuration file example. So this is loaded by container runtime when it starts up. And this specifies different block.io classes into which containers can be then assigned to. So here are two examples where the high priority class sets a IO scheduler weight that is high above the normal, the default, which would be 100. And then there's a throttled class, which has two sets then defined under it. So the first devices picks up all devices that are all block devices that are not partitions, but they are like whole devices, because you can't actually throttle partitions separately. So you can only throttle whole block device. All partitions then obey that. Okay, so that matches. The first one matches all the devices, and the second one then matches all the devices which have SSD string in the device ID. So it sets a bit higher throttling values, 8 megabytes per second for SSD disks, and then normal hard drives would get 40 megabytes in this example. So this is loaded by the runtime, and then the next slide shows again that how it is used in the pod spec level. So here in this example, there's a database servers pod, which includes 2 server containers and then 1 backup container that would be running backups, for instance, in the from the database server containers. And priorities are again in the annotations. So here you can see that block.io default class for all containers in this pod would be high priority, and then particularly set to this backup container, there is then the block.io class throttled there. And this also then shows that you can actually configure also RDT classes, of course, at the same time. So this gives quite fine-grained granularity in this QoS sense, that how you can allocate and how you can control how these resources are used between workloads. And hopefully the result would be that if you have performance critical workloads on your node, then you would be sure that it will get the hardware resources it needs. Because, well, currently the situation is that you can assign like dedicate CPU cores to some workloads, but anyway, those workloads would be, of course, sharing both CPU cache and also block.io bandwidth with other workloads. So our goal is to help people to get these resources shared as well.
So on current implementation side, what we have? We have for both of those, for cache control and for block.io, we have open PRs for CRI-O and containerd. It's exactly implemented like we showed in the presentation. So we have configuration files, which is, we hope, user readable and understandable. We have a small library. Right now it's on the Intel GitHub area. It's called Go Res Control. But we really hope what this library will be contributed to open containers or to any other similar place where all runtime can reuse this piece of code. Because practically the pieces of the code in this library is parsing those configs, and when doing we needed res control, res control kernel configuration, and when modifications related to like processing the annotations, processing the OCI edits for those parameters. So if you have interest in any of those topics, please join our discussions with runtimes. And what, beside those two PRs, what we have in mind is actually the steps how it get it as a like normal usable thing inside the Kubernetes. So right now we are in phase 0. So we are thinking of using annotations to pass the class parameters. So just to give a possibility for runtime to implement the bottom layer of these features and give people to ability to try the things. Second stage, what we thought would be to start adding those class fields in the protocols when the Kubernetes is talking to runtimes. So for CRI protocol, it means what we would like to have a dedicated fields like currently seccomp has for both container level and pod level. And at this stage, we still will be able to use the annotations if those fields are not populated by the kubelet. And as the latest state, we hope to get the pod spec changed so the users can use those cache control and block IO fields as a first-class citizen in pod spec. And at that stage, we think we can drop support of all the annotations. So that's practically it, what we had for today. We wanted to show it. We wanted to share our progress in this feature, and we wanted to ask for feedback and participation into pull requests and in discussions about those topics.
All right. Yeah, thank you. This is very informational. I mean, it seems like a lot of work going on, you know, behind the scenes in the runtime. And one question that I have is, you're working with the Kubernetes community to maybe Signode to make this more of a first-class citizen in the long term.
Sorry. Yes, we need to do it. We first created those pull requests for runtimes just to get like overall okay, not okay from runtime people, because practically implementation of this scale require commitment from the runtimes to support it. The Kubernetes side, yes, definitely, it also need to have a commitment for adding field or adding well-known annotation, but yes, it's in the pipeline.
Yeah. And a note regarding RDTs also that kind of the runtime level support for RDTs quite small patchet, and the OCI level already kind of supports these RDT classes, but it's not supported by the container runtimes. So runc does that, but the container runtimes don't. So we kind of wanted to have the container runtimes on the kind of same level of support that runc has. Just a note.
And by that you mean cryo and containerd, right?
Yes. Yeah. Cryo and container.
As a first implementations of container runtime, yes.
What's the time frame for those pull requests to go into CRI-O and Containerd?
We want, of course, it's like as soon as possible, but it all depends on well, feedback from the community. What yes, we wanted. Second, it's bandwidth of reviewers and approvers in those projects to get it in.
Got it. I think Derek, are you one of the maintainers for Containerd?
Yeah, I'm taking a look at the PRs now. I hadn't taken a look at them yet, so hasn't really been on the maintainers' radar much, but I can ask other maintainers about it. See.
One of the reasons why we came to this meeting is what we wanted to bring attention to these functions from the people who are working on different runtimes.
What is the primary use case? Do you have maybe some end users that are interested in this feature?
Yes, for different, well, for cache control, it's primarily network operators who are interested in the separation, because the network function workload require like highest possible performance. So in ideal case, the exclusive allocation of the cache and nothing else supposed to be using the same cache lines. When we had our customers who wanted to use like free capacity of a cluster, so meaning like he has a normal workloads, but when he has kind of like low priority workloads, what he wants to run during the night when the like load is not that big. So like this cache separation is helping to a bit isolate with, well, like make sure what the hardware assists with low priority on those things. For block.io, it's both in community and like some feedback from some other customer was like the scenario of applications which are dealing with, for example, like live streaming. So you have like big arrays of data, for example, like some TV recording or like sport event recording. And when the front-end servers like pushing this data, and when you have additional like all kind of like maintenance tasks like loggers and a bunch of other things what doing in the background. So where people wanted to separate what this like live streams get the highest priority of disk bandwidth, and when all kind of like support jobs in the background should be throttled to particular like subset of IO bandwidth.
Makes sense. Makes sense. Yeah.
So it's all about the prioritizations of workloads, and the examples what we showed, like you can have it either similarly to what Kubernetes is doing for like normal workloads, like guaranteed burstable best effort split, or you can have based on let's say like based on how much the customer pays for the resources. So you can have high priority customers what will get as much as we can, and when you can have like development or some like canary deployments which can be throttled. One of the examples.
Yeah.
Or a mixed setup.
Yeah, exactly. So yeah, so I mean it's similar to the idea of having, you know, memory CPU limits, requests and limits, right? So then you have some sort of
yes and no. The biggest difference between all of those is what like in case of memory and CPU, you just specifying how much you want and you have exact amount, like how much you have. Here, both for cache and for block.io, you don't really have, like you cannot like split or request particular amount and say like, okay, this will be used by this workload and nobody else is going to use. It's well, it's not granular enough to that level of control. And in case of block IO, you cannot really request something. You can just only limit maximum, and that's it. Or you can have a priority, but again, priorities is just like arbitrary numbers, but it's not really a countable resource.
Got it. Yeah.
And in the case of RDT, there's this kind of hardware limit that the number of different configurations of classes is really limited to something like 16 or so, depending on the hardware.
Yep.
And
Okay,
with all of this, what we wanted to solve is practically two big use cases. One is for user to get it easily consumable, this kind of resources. And second, for sysadmins, if we have a heterogeneous cluster, when we can create a config files with different like parameters tailored for particular node, but still have the same like class name for the resource. So it's flexible enough to cover pretty much any setup.
Great. Yeah. Thank you for the presentations. We're out of time, so we're like at 9:01 Pacific time. But yeah, so the video will be posted online. If you could share the slides, then I can post it on the meeting notes, and basically that will give it more visibility, hopefully give it more visibility, and hopefully you can get your things moving also with Containerd and Cryo. But you know, if you need anything related to pushing it forward, feel free to reach out, you know. So, and I know you're also in the container orchestrated device working group, so we can keep in touch. Well, thank you all, and yeah,
Okay.
I'll talk to you soon.
Thank you.
Bye.
Okay,
Thanks
thanks.
for your time. Bye.